Now, yes. Okay, excellent. So, yeah, now welcome Kristian Knakkergard and Wilson, who will be discussing dynamical pairing by disorder of tokens in the magnetic pattern.
Thank you. And thank you for the organizers once again for organizing this very nice event. I should use the microphone, I guess. Is it on? Yeah. I, of course, have the very, very questionable honor of being the last speaker of the day and for the dinner tonight. I'll try to keep it as light as I can. I'm the third yearist in a row to give a talk, but there won't be as many equations as to I can assure you. Right. So my talk is about pairing. So let me start. Okay, it's not doing anything. That's okay. Good. It's about pairing, and let me start by talking about sort of the prototypical pairing by order. So the prototypical example is electrons in an ionic lattice. And right, the distortion of the lattice leads to an induced interaction between the electrons, three electrons moving around. This leads to Cooper pairs, and as most of you probably know, to conventional superconductors. Right, and in the context of these kind of doped magnets, they have been, so the pairing of dopants in these kinds of systems have been proposed as a mechanism behind high-TC superconductivity. So here I'm showing like a phase diagram for a specific group oxide superconductor, sort of the typical superconducting domes here. And so again, sort of the mechanism behind this could be that you have these dopants that distorts the magnetic background, and then that leads to induced interaction between the dopants that leads to pairing and thereby maybe to superconducting. Now, the system that I will be eventually talking about is a ladder system, and let me just stress that these kind of ladder systems actually naturally arise in materials. Okay, and then on the sort of the quantum simulation side, which is sort of more the direction that I'll be taking it, there's been some recent very nice development where pairing in like a Heisenberg ladder has been seen. So this is an experiment from the Bloch's group where they looked at how dopants, so holes in the system, pair up. And they say essentially the physics in this ladder is described by a lattice that has a strong translate coupling, spin coupling. This leads to the formation of these singlets. And then as these dopants move apart, that leads to basically a linear increase in the energy. Okay, and so this kind of effect is realized at low temperatures, where the temperature is small compared to the spin coupling. So like this kind of pairing by order mechanism, right, is essentially that you have some potential energy that tends to rise as the particles move apart. And so you have energetics that sort of tries to push the particles back. But now what I'll be describing to you is that there could be a different mechanism, what I'll be calling pairing by disorder, in which as the particles move apart, they fluctuate a lot in energy, and these fluctuations actually pushes the particles effectively. Right. So the specific system that I'm looking at is this kind of ladder geometry. It's a simplified interaction, so an Ising interaction, and then it has hopping, correlated hopping, such that the strings can only hop onto vacant sites, here shown in green. And so this, kind of importantly is that I intentionally shut off the hopping across the ladder. This is mostly as like a theoretical simplification. And so the kind of dynamics that happens in this lattice chart is that these holes effectively move around. Okay, now importantly, and what I want to specify right away is that this is actually, even though this might look a bit artificial, it is actually implementable experimentally. So, for example, the 1D motion of the holes was realized in this experiment with the Heisenberg level. The easing interactions can be induced by using so-called Rydberg pressing, and the sort of the non-equilibrium motion of the holes can be tracked with like using single-site resolution. So all these ingredients are in place to actually see this kind of stuff. And for now, let me just do like a detour before I get to like an experimental implementable case where there's just the nearest neighbors. So I'll dive right into some results. So what I'm doing is that I'm taking an infinite temperature spin ladder, so completely disordered, and then I'm pulling out two spins from the two central sides here. And so the initial hole correlator, so I'll use these coordinates x1 and x2 for the position of the holes along the ladder. So the initial hole correlator is just the dot in the center. And then I'll compare that to like the free motion of these two holes, which, for example, happens in this kind of experiment. So the initial dynamics looks very much like the ballistic behavior seen for the free motion case. But you can already maybe start to see some deviations here. And then as time progresses a little bit more, what you see on the free motion side, right, is that this ballistic motion just continues. But over here, you have like two features. One is that the maximum keeps being in the middle, and the other is this correlation of the coordinates. So they tend to be along this diagonal. And so this correlation is basically measuring that these holes are actually pairing. Right, so how does this actually come about? So what we're doing here again is that we're putting two holes into an infinite temperature spin background. So we have all these different realizations of the spin background that are realized sort of simultaneously, and then we have to average over all of this. And so what happens energetically as they move apart is the following. So as they move, they have this fluctuating energy because there's these pairs, for example, across the ladder, will increase or decrease in energy sort of randomly. And if we just expand the view here, this like fluctuates up and down. And if we look at a bunch of realizations of this, you see that this is sort of spreading out as the distance between the holes goes up. And what you might be able to see here is that the mean of this is 0. So on the mean, they don't see any inducements, actually, so to say. But there are heavy fluctuations. And actually, the fluctuations, they increase as a square root, essentially because the potential, the values of the potential performs a random walk. So what happens dynamically is that as the two holes start to try to move apart, they come in with some initial kinetic energy, and eventually this potential will fluctuate to a high value. And when that happens, the holes will back reflect or backscan. And so this is basically the pairing mechanism. Now, they were also what you could sort of hint at in the previous figure that I showed you is that they are localized. And so actually what happens as a function of the center of mass, so the center of mass x here, there the sort of the potential is actually bounded. So as you move a pair along, the potential energy does not fluctuate to higher and higher values. But what happens there instead is that there are many ways in which the two holes will propagate to another side. And through all these different pathways, they will see a different energy shift for each. This leads to destructive interference of the pathways, and it's basically the physics of Anderson localization. So they are the center of mass is Anderson localized, and they pair up into backscatter. Right. So let's look at some more results here. So here it's again this whole correlator calculated as a function of time. We can also look at like what happens to these center of mass and relative distance coordinates. So what I'm calculating here is like the RMS distance and RMS of the root mean square of the center of mass. And if you maybe just for now focus on the purple lines, what you see is that the center of mass increases to much larger values than the relative distance between them. So they propagate much further into the lattice than they separate from each other. Another way to measure this is through this correlation coefficient, which is basically just measuring sort of a normalized correlation between the coordinates x1 and x2. This takes some values in the interval between -1 and 1. And negative values correspond to repulsion, positive values to attraction. And so what we see here are these positive values. And for the purple line here, which is for a specific where the intra-leg spin coupling is 0, this rises almost to a unit value. So these are very strongly paired up. They very strongly want to be on top of each other. And then a final measure that we can look at is basically this relative hole correlator, which is measuring how much more likely is it to see the holes on the same rung compared to what you expect from their margins, so from their individual distributions. And so here this can like easily rise to a factor of 4. So it's 4 times more likely to see them as a pair than what you expect from the margins. Right, and then I think I'm gonna rush a little bit through the steady state stuff, but what we can do is, so this was for a specific value of the spin coupling across the ladder. And then we can basically extract, so there's a steady state along times shown here in these dashed lines. And we can map out, so this Lx and L delta are basically the asymptotic length scales in this top plot here. And the light purple one here is for the center of mass, and then for the relative distance below. So again, there's a big gap between these. And then if you look instead at the case where the spin coupling in the leg is equal to 1 across the leg, this difference is smaller, meaning that the pairing is weaker in that case. And we can map that out again by this correlation coefficient as a function of J perp over T. And actually interesting, what we see there is that when J perp is large, the pairing is again very strong for this case where there's no intraleg spin coupling. But then as you decrease J perp, actually the case where you also have spin coupling in the legs actually pairs more strongly in the sense it become comparable. And similar things are seen in this relative hole correlator. Right. And then finally we can map out this spatially. So here is this relative hole correlator in the steady state as a function of delta, so interval distance for different values of J perp. And there is, so what you see here, right, is that there is like a small, here there's a bigger discrepancy than up here. And that basically is like a short range effect that like over all these two lines are very sort of similar to each other with this low value of the curve, but at short range they still. Okay, so that's very nice and neat, but can we actually see this feasibly in experiments? And the method that I'll be describing to you the last sort of 5 or 10 minutes of my talk is using Rydberg risk. And now here I actually wanted to make like a throwback to a talk yesterday by Luca, where he talked about core molecules and kinetic atoms, and I would say it should be possible to implement this kind of scheme using these methods as well. But I'll stick to this Rydberg risk. Right, so what is Rydberg risk? So what you see here is sort of the spin states that we're interested in, spin down, spin up, the red and blue. And then what we want, so these are initially non-attack. And then what we want are these easing interactions between the spins. And then what you can do is that you can couple this to a higher lying Rydberg state. So this has these Rydberg states that were also discussed earlier, has these van der Waals interactions, 1 over R26. So as the particles move together, the spin up state that is now coupled to this Rydberg state inherits some of this interaction, and their energy will shift. But then what also happens actually as they move together is that this drive becomes more and more off-resonant. And so instead of like this divergent character of the interaction, you get this soft. But besides that, you get this kind of interaction. So the form of the interaction is this kind of fully polarized one where you only have interactions that spin up, and it has sort of this structure. So something like this. Right. And sort of thanks to some experimental colleagues who were gracious enough to calculate this, we can actually map this out exactly. And there's a nice tuning up here, which consists in the tuning of this drive, the bad tuning of this drive that you can use to sort of shift this up and down. Now, what turns out to be a very nice trick as well is that these states actually have like a spatial dependency. So this higher lying state is a P state. And so there's a directionality to this interaction. So this upper case here is actually where the P orbital is in the plane of the ladder. And there it's like the interaction is an isotropic in the ladder. It's only a function of the distance. But then what you can also do is that you can rotate the orbital, which is an external magnetic field, down into the plane of the ladder. And so that weakens interactions here. So on the same length scale, the interaction will be weaker, as you see. Right, so that's a nice tuning that we can use. Okay, and then how do you actually see the kind of physics that I've been talking about? So the sort of simplistic experimental sequence that you would have to go through it goes as follows. So first, you prepare all atoms in the spin down state. And then you have like repulsive laser potential on these two central sites to avoid that you have spins there. Then you rotate all the spins locally to be an equal mixture of spin up and down. And then finally, you sort of switch out these local laser potentials and let the holes move. Okay, what is the reason for like doing this complicated sequence? Well, essentially, like controlling So you cannot just crank up the temperature in this experiment because this effective model would eventually would break down actually at high temperatures. But during this sort of state manipulation instead, it turns out to realize exactly the sort of the infinite temperature hole dynamics. Right, and so how does this actually look for this experimentally feasible case? So here are results on a finite lattice of 21 by 2 size. And what you see first in orange is this isotropic case where the orbital, the p orbital lies in the plane of the ladder. And there it's like quite hard to actually see this pairing as there, but like this correlation coefficient is quite low. And the relative pole-hole correlator does go slightly above like what you expect from the marginals, but not by much. But then you can use this trick of rotating the orbital down such that it's perpendicular to the ladder. Oh, sorry. And then what happens there is that you get this case of strong rung couplings. So the coupling along the rung will be much stronger than along the ladder. And in that case, you get into the scenario of much stronger pairing. And the correlation coefficients jumps up, and so does the relative pole. So this should actually be very feasibly seen in experiments. Okay, and let me end my talk with a few perspectives. So what you've seen, right, is a very simplistic example where the pairing of particles does not come from the sort of the energetics pushing them together, but the fluctuations in the potential energy. Now it turns out that the model that I've been looking at actually is called a fragmented model. So it has Hilbert space fragmentation. At the moment, it's not clear to me like what is actually the role of this. Is this essential for the model? And so a nice future prospect would be to break this fragmentation and see what happens to this pairing. What you can do, for example, is that you can look at 2D motion, look at a fully 2D lattice and look at motion in 2D. This breaks this fragmentation. And another thing you can do is put in spin exchange, super exchange terms and see what that does. And then finally, what is sort of also an interesting question, I think, is that for now, these fluctuations that we saw are essentially classical fluctuations in how the potential varies. And then it's quantum evolution of the holes in that classical disorder potential. But could you realize something similar with quantum fluctuations? Okay. And then one might ask, okay, what happens at lower temperatures? So what I've recently looked at is motion of single holes in these kinds of systems. And there is like localization effect. It actually turns out to be extremely robust. So if you're, for example, on the ferromagnetic side, so you decrease temperature to the left here, it turns out that the holes only like asymptotically delocalize at low temperatures. Both in this ladder geometry and in like a mixed dimensional case where the hole still moves along one line, but you have a full 2D lattice. And so a good guess for what happens is that as you diminish the temperature, then on the ferromagnetic side, you would sort of see asymptotically free holes. But that would still pair for any non-zero temperature. And on the anti-ferromagnetic side, so going to the right here, what happens instead is that you build up a checkerboard pattern that will actually bring back this linearly growing potential that I showed you initially at low temperatures. So there you can see like a crossover to like a confinement of these. That would be the guess. Okay, and then finally, let me just flash a couple of other projects that I've been involved with recently. So there's a very nice experimental work by the group of Art, in which they use quantum beam spectroscopy to look at the repulsive side, so repulsively interacting impurities with the background BC, and use this beam spectroscopy trick to get out both the energy of the attractive and repulsive branch. And then I have another recent paper where Jens here, who's now graduating from his PhD, was sort of did all the work, but where we look at how the dopants in the spin liquid can be used maybe as a probe to look at a transition between an anti-ferromagnetic phase and a quantum spin liquid. Right, that's it from my side. Thanks for your attention.
Thank you very much, Doctor. I don't know if I have missed something, but this mechanism, they say because when at 4 volts, basically it has a sort of random changing images for the different configuration. So up to which point you are just feeding one hole alone, and it's just because you have the two together that they are remaining up there. So my point is, at which point is you are failing them, we're just not letting each one of them evolve. Sorry. So my point is that you keep them together because each one of them is so alive, but not because they are not.
No, okay, so that's exactly why you need to compare this to like what you get from the marginal distribution. So you look at, okay, how do these holes move if you ignore the other one, right?
Exactly.
And the point there, right, is that, so for example, here, that's exactly what this relative hole correlator measures. It measures how much more likely is it for them to be at a certain distance than what you expect from the margins. Okay, so this is exactly measuring this point that, so here, for example, this rises to a value above 2, so it's 2 times more likely to see them on the same run than what you would expect from just observing the holes individually.
Because if you look at the Anderson like compensation, would be good even for a single one up to some point, no?
Right. Okay. So the point. Okay. So another thing So another point or another way to understand this, right, is that I can move the pair along, and if I do that, the potential has this sort of bounded behavior. So it can fluctuate basically between minus 1 and 1, and it's stay parallel. But if the holes start to move away from each other, these fluctuations actually get worse and worse as they move. So they want to stay together as a pair because in that way they avoid as much fluctuation as possible. There are 2 chargers without the owner. One is mine. One is mine. What is it? On the